All right, it is 10:31. Okay, so we're going to talk about Newton's gravitational universal law of gravitation and a little bit about inverse squares so that you guys can kind of understand a little bit more about what the assignments are supposed to be. So first off, the apple and the moon. So Isaac Newton realized that the motion of a falling apple and the motion of the moon were both actually the same motion, and it's caused by the same force. And that force is the gravitational force. All right, so whether or not you know this, the moon is always falling. The reason that it doesn't fall on us is because of the way, hi Portia, the reason that it doesn't fall on us is because of the way that it orbits around the Earth. Okay, so the Earth and the moon are pulling each other pulling towards each other, but it doesn't fall on us because at the same time the moon and the sun are pulling towards each other, and all of this is causing a rotation. So Newton's idea was that gravity was a universal force and it was acting between two objects. And those, when you think about it, let's think about us on the Earth. When you think about those two forces, um, the gravity is pulling us down, and then there's a force pushing up on us. So there are two forces acting on any object. Okay, the universal force acts on any two objects. So between the moon. Oh, yeah, you are. Lexi was supposed to be in here, but she's not. Oh, there she is. So now there's two. And I have no idea where, hi, Lexi. I don't know where Jamie is. It's really hard, I think, for them to remember because of the new rotation thing, but they'll get it. We'll get it all together. Anyway, um, Newton's idea was that gravity was the universal force, so it's acting between any two objects. So the earth and the person, the moon and a person, the moon and the earth and the apple and the person. So there's always two things. Okay? All right, let's go on. So at the Earth's surface, Newton knew the gravitational force on an apple equals 9.8, right? And that is in SI units. If you're talking about units in the United States, they say 32.2 feet per second squared. 9.8 is what you're going to be using, I don't know, 99% of the time. So remember from last time, your weight is equal to your mass times gravity. So anytime you want to figure out what your mass is, all you have to do is weigh yourself and then divide it by 9. Well, on Earth it's going to be 32.2 in America, anywhere in the United States. Then everybody has a mass. And just real quick from all of our other information, does your mass ever change? Type that in there. Tell me. Yes or no. Does mass ever change? Well, okay, let me put it this way. Does mass ever change from one type of gravity to another? Oh, yes it is. Maybe it's just not loud enough. Can you not hear me at all? It says it's on. Okay, hold on one sec. All right. How's this? Can you hear me now? Hello? Okay, I'm talking. Can you hear me? Yay. Okay. All right. So I could go back, but what we're going to talk about is that there is a force. There's a force between any two objects, okay? And that force Newton decided was gravitational force. And it equals 9.81, and that is SI units. Oh, all right. So SI units are the standard something. I can't remember what it's called. But that's what, meters. That's where we use meters and centimeters and kilometers and liters and all that fun stuff. In the United States, what we use for gravity is 32.2. So what I was talking about was that everything has a mass. So if you want to find out what your mass is, you can weigh yourself and then divide it by 32.2. And then that would be your mass. Now, if we were to take you and then shoot you out into space, the question that I'm asking is, after you've weighed yourself, you find your mass, shoot you into space, is your mass ever going to change? Does your mass change? You guys can hear me. Answer. Okay, Portia, you have two answers. I wish there were a little time over there that tells me when you answered. So, no, your mass doesn't ever change. Your mass is always the same unless, your weight changes. Then your mass is going to change. That's right. What's going on? All right, hold on one second, guys. This is physics. Requires flash player. All right, so for right now, why don't you just listen, and then, I don't know, maybe next time, are you in Google Chrome? No, you're in Firefox. I think Google Chrome has the flash player, but I'm downloading it. So right now you can just listen, okay? And then you can look at my pretty pictures. Okay, guys, sorry, we had a new person is actually here. He's not in here because his computer doesn't have the flash player, but his name is Paul. So everyone say hi to Paul. I don't know if they can hear me. I have questions about that. My mic may be really delayed. Okay, never mind. All right, guys, let's go on. There. Thank you, Portia. All right. So let's talk about some weight on the moon. So Newton reasoned that the centripetal force on the moon was also supplied by the gravitational force. So centripetal force, does that equal to mass times gravity? So when you think about it, centripetal force is that force that's pulling you towards the earth, or the moon toward the earth, or the earth toward the moon, okay? As the moon rotates about earth, it's always being pulled in toward the earth. That is the acceleration due to gravity, okay? So what we want to know is that really true? Well, Newton's calculations showed that the centripetal force needed for the moon's motion was about 1 in 1/3600th of moon mg. However, where m is the mass of the moon, okay? So that's the mass of the moon times gravity. So Newton knew that the moon was about 60 times further from the Earth than the apple. So 60 squared is 3,600. So this is how we came up with this formula that you used in, I think, the second practice. So from this, he reasoned that the gravitational force is not constant. In fact, it's a magnitude of the force inversely proportional to the square of the distance. Okay, so if we look, Lexi, I don't know what to tell you. I think it's your headphones. Okay, so Newton concluded that the gravitational force is directly proportional to the mass of both objects and inversely proportional to the distance. And what that gets us is this equation. So the G is a constant. It's a constant of proportionality, and you guys have learned this in your math. You have that K value or A value, which is a constant of proportionality, and that's what this G term is. This M would be the mass of the Earth, or one of the masses, doesn't matter. You can use this for any two objects that are pulling toward each other. This is just a different mass than this smaller mass. And then the radius squared, because if you remember, 60 squared is 3,600. So this, when your variables are both in the numerator, that's a direct proportion. And when they're in the denominator, it's an inverse proportion. And in this particular case, it's squared. So for your first problem in this new quarter, it talks about graphing that inverse graph. And what you should get, let's see if this'll, okay, I don't know if it'll, right. Okay, you should get, all right, it's not writing, come on, we can do this. All right, you should get a graph, right? And your graph down here is going to be, I believe this is going to be distance in meters, and I can't write very well with this mouse. And over here, it's going to be gravity. So it starts at 9.8, right? Okay, that's terrible. But your graph should look like this. And that is what an inverse graph looks like. All right? And definitely an inverse squared graph. All right? Does that make sense? So that gives you guys, if you haven't started on this quarter or this week's, that's what your graph is going to look like from the first question. Does that make sense? Okay. Must be delayed. So whenever you go into your the first quarter and the first week, the first question is going to ask you to graph something, and this is what, oh, now it's drawing.
I have to start from the first quarter?
No, it's second quarter, okay. First week. And that's what that graph is going to look like, okay? All right. So the inverse square law, Newton's law of universal gravitation is often called the inverse square law, and that's because the force is inversely proportional to the square of the distance. So one of the questions on the second practice asks if you have a distance. Let's see if I can, I'm drawn. Nope, it's not drawn. Okay, so if I have a distance, so some distance here, right? And if I double this distance, so I have some mass here and some mass here, and if I double this distance, what happens to the force? So I want you guys to think about this. Your force, it's hard to write with my finger, due to gravity, all right, is equal to this radius squared. And if I double the radius, I'm going to square, oops, that whole thing, that's horrible. So I square the 2 and the radius, all right? So that means that if you double the radius, then the force is going to be lessened because your denominator is going to be bigger. So the force is going to be less by 1/4. Does that make sense? Yes? No? Does that make sense to you? Okay. All right, sorry. Okay, I'm just going to go to the next one. So, and again, this is a picture of what the graph should look like whenever you get to it. Okay, good. So this is the distance between objects, and okay, and this is the gravitational force between them. So your graph should look similar to this one. All right, these numbers are not going to be the same. You're going to have different numbers here, but your graph is going to be this type of steep slope or a steep, I don't know, someone else called it like a ramp, you know, a really steep ramp. Okay, and I think, so hold on, I think this is the last one. So the law of universal gravitation allowed extremely accurate predictions for the orbits of the planets. And that's how they came up with, you know, that the planets orbit, they don't orbit in a circle around each other, they orbit in an ellipse. And if you guys know at all what an ellipse is, do you know? Yes or no? Do you know what an ellipse is? Okay, so okay, circle is around, oops, I don't know if I can draw a circle with this. Nope. Okay, I'm going to draw a circle. There's my circle, and an ellipse is an elongated circle. That's not even good. That's better. That's an ellipse. All right, so it's an elongated circle. And that's how they figured out that it was an ellipse instead of a circle, that everything rotated about the sun. Alrighty, guys, so that's it. If you have questions on the assignments, please make sure that you send me a message, and I will be more than happy to help you, especially with that graph. You can do it pretty easily on Excel. If you need some help with that, let me know. All right, anybody have questions? All right then. No questions, you can go, and thanks for coming, guys. If you have questions on your assignment, let me know. Okay? Okay. And I think if you have any more webinars today, you should be able to get in there with that. Yeah.
I don't think I have any more.
Okay.
Most of mine was earlier this week.
Okay. And you just started, right? Oops.
Yep, Monday.